I'm going to write again this one, but I'm going to make it a little bit more obvious what this is. So here we're writing the same thing, and as you may see, we have a gradient of a divergence. So the divergence of the displacement in this case is the volumetric strain. You see, there is a variation with respect to x1. Okay, now what I like to do is I like to group some of these guys according to what they have in the numerator and denominator. So you see that this one, you guys didn't tell me I was missing this one over here. You see that here we have u1 respect to x1, u1 respect to x2, and u1 respect to x3. So those all look very similar, and we can group those three into just a simple term, which is going to be, notice something else. Here you have a 2, and the other ones you don't. All right? So from here, I'm just going to take one of those. Okay? There is one left. But I can write mu Laplacian of u1. Those are those three terms together. These two and one of these. Okay? And I have still the other terms. Notice, let's see what we have in here. We have u1, u2, and u3. And each of those has a mu in front. So there's going to be a mu in front. And those two have a dx1 over here, right? And by the rule of partial derivatives, I can write this as dx1, and that term over there is going to be du1 dx1. So it's exactly one of those. The other one I didn't take. So the other one I didn't take is that one, and then I'm going to put this one and this one. And the second term, I already took this one out over there. So this one is going to be u2 dx2 plus the last one, du3 dx3, which is that one over here, plus f1 equal to 0. Okay? And now we're pretty close to our solution. Let's see. Do you see something that looks the same or somewhere over there? Let me erase this so we don't have to erase those equations. What did you say, Michael?
Inside the brackets and then the last term before F1.
Those are the same, right?
Yeah.
So these two are divergence of displacement, right? Volumetric strain. And this is a variation with respect to x1. So that's going to be a gradient. So I can write those two terms as lambda plus mu. Let me write it a little bit closer to the left. Lambda plus mu, the gradient of the divergence of mu. That's the first term, but now expanded in 3 dimensions. Okay? And you any question, Robert? It looks like.
Well, yeah, because I'm looking at the equation we wrote in the simplified form on the left, right?
Yeah.
Where we're writing that we have the gradient of u plus the gradient of the transpose.
Yeah.
So the constant matrix from the distributive equation is just a constant, as in 1/2. And is it divergence distributive? So if I look at just the equation to the left, wouldn't I expect to have 1/2 times the constant times the Laplacian of the displacement plus the Laplacian of the displacement's transpose?
If you wanted to work just with these equations, but
Yeah.
you could do that, but then you bump into this C, right? That you could do the same thing that we have done just with those equations, but you wouldn't be able to simplify it as we're going to do right now, just in terms of the displacement and with these 2 simple coefficients.
Okay.
So let me finish with this. So we said that we're going to have, I'm just writing in red because it looks a little bit better.
Because I would expect them to come out to the same thing.
Yes, you will come up to the same thing, but when you bump there into a C, you cannot really do that. You know, you will have to solve like 3 equations simultaneously. That's going to take a long time. It's the same thing as this. We're just solving one of those equations. And so this one is going to be that one and this one. And then I have this guy over here, this one, that is just going to be mu Laplacian of the vector plus, and now I recover the vectorial form of f equal to 0. And this equation is what is called the Navier's equation of linear elasticity, where our unknown are the displacements. As long as you solve that differential equation and you figure out what the displacements are, that's everything you need in order to solve stresses for arbitrary shapes, arbitrary boundary conditions. It's everything in there. The problem is how to solve that equation, which is not, it is not very straightforward how to solve those equations. So there are several methods to solve these equations. We're not going to go in detail through those, at least to the analytical equations, because you have to be very good in math in order to do that. And I know you guys are good in math, but we're going to need a lot of time in order to do that. So we're just going to go briefly through this, okay? So if I talk about analytical solutions, we have to talk about what are called the Beltrami Mitchell equations, which are known as a compatibility equations. And this refers to compatibility of strains and deformations. If I were to give you a displacement field, can you calculate what is the strain field, which is a result of that? It's very easy, right? It's just the equation, the strain tensor, derivatives, what we have done over here. So strains, derivatives, that's it. So to go from displacement to strains is straightforward. You don't need a lot of things in order to do that. You have the equations, That's it. However, if you're solving strains and you need from here to calculate what are the displacements, this is not straightforward at all. Okay, because you may have multiple solutions for that problem, or in some other problems you may have some incompatibility of displacement with strains. And that's why it is important that when you solve these equations analytically, the first thing that you do in order to reduce your number of equations, you comply with the compatibility equations. Which are the compatibility equations? It's just a set of cross derivatives that allow you to simplify the solution to obtain a compatible deformation. Otherwise, you're gonna need some information in order to solve your problem. Another method to solve these analytical equations is what are called the Airy's equations. Basically, what Airy proposes is a function, a sort of a potential function, for which you can calculate a double Laplacian respect to this function to be equal to 0. This is very similar to computing flow networks, okay? Or when you solve for principal stresses. Well, let's come back to flow networks. You know, when you solve for flow networks, you have two families. The family of equipotentials for pressure, and then perpendicular to that, you have the lines for flow. This is exactly the same thing, but instead of solving for pressure and flow, you solve for stress, in which the second derivative of this potential function respect to x1 gives you sigma 1,1. The second derivative of potential function respect to x2 gives you sigma 2,2. And the cross derivative of this phi respect to x1, x2, you guess what do we get? Sigma 1,2. And it's like that. You just propose a function, and you look for the actual shape of the function that it gives the solution.
There should be squares in the denominators of those two sections, right?
Thank you very much. Yes, I always forget about those. So yes, so that's the second derivative. Okay, so if you are into analytical solutions, then this is the way you have to go. And if you need some additional literature that you would like me to point you to, just let me know. The book of Malvern is very good for that, and there is a little bit also in the book from Jagger. But as I told you before, we're not going to solve those, but we're going to use them. Those analytical solutions are especially good in our times to verify our numerical solutions and our approximations. Within those sets of analytical solutions, later on we're going to use the solution of Kirsch for stresses around the wellbore. And I forgot to talk about the project. So the project is about this, okay? So as soon as I finish this, we'll go to the project. Kirsch solution is based on these methods, stresses around the wellbore. Griffith solution is for stresses around a crack at the tip of a fracture. And also, we're going to talk about Snedon's solution, which is stresses around a fracture, around the face of a fracture. And if you don't have the nodes, so I guess I have to pull them out, and I cannot use also the projector. So, but you have, let's look at the project. So get one of those copies, and let me find one here in my notes. Okay, here it is. And while that, I'm going to turn on the computer. Okay, just give me one sec. How was your weekend, guys? Good? I know we're far from the weekend, but I didn't see you on Tuesday, right? I was in Dallas. I saw Min over there. Min and Siha were there.
How was that?
Anyone else? It was good. It was a good meeting. All right, so you have the project, okay? Here we have two problems. One is to compute the stresses around a wellbore, and the other one is to compute the stresses around a fracture. For that, I want you to calculate the solution with a numerical method using finite elements. And for that, you're going to have to download and install this software, which is called FreeFem++. And if you go over here, you will see this is the software, and you can download. There is a download link over there. Can you see all of that there? No. Okay. Okay. So I don't think we're not going to have time today to talk about finite elements, but this project is going to be due next Friday. Okay, so you're going to have time for that. What I recommend that you start doing is, if you don't want to get into the numerical part right now, is to work on the analytical solutions. So that's what we talked about today, the analytical solutions. And for that, I'm not going to give you the equations here in class in detail, because I think that's something you can go on your own, and it's very easy. For the stresses in the face of the fracture, you have them in the back over here. And so you have here sigma yy, displacement 2. And for the stresses around the wellbore, those are the so-called Kirch solution. They're very easy to find in the internet, but I have also uploaded a copy over here. If you go to projects, and if you go to FreeFem tutorial, let me open this. Okay. Okay, just give me one sec. All right, so here you have a summary of the equations that we have seen. This is the theory that we just saw. You put all of that together, and we're going to talk about this probably next class. I don't think we're going to get to there today. But if you go a little bit lower, here you have the analytical solutions for the stresses around a cavity. Okay? And with these equations, you can start solving the problem, at least the analytical part. And these are the so-called Kirch equations. And later, you're going to have to solve that numerically. Let me see if there is something else over here. I don't think so. It's just a numerical part. So probably we should talk about the numerical part. Okay, since I have opened the computer, I don't know if you know these guys, but I sent you an email. I hope you read my emails. That I have uploaded the class videos, and you can go over here. It's in YouTube. Unfortunately, there are some of those that have no audio, or the audio is not working great. So that's something I have to fix. All right. Or I'll see if for some of those I add subtitles to make up for that. But remember that we have an exam like 3 weeks from now or so. So it's important that you start trying to review some of these concepts. Okay? Okay, so we talked about analytical solutions. Let's talk now about numerical solutions. Let me turn this off and move this out of the way. Analytical solutions are very good for solving simple problems, but for a more general problem, we always have to go to numerical solutions. And the numerical solution is just going to be an implementation of a numerical solver to solve that equation, but it's exactly the same equation. So what kind of methods do you guys know to solve differential equations? I should have deleted this one. Anyone? Finite differences. Very well. So let's see, we have a space here to talk about finite difference. So we're going to talk now about numerical solutions, and the first one is going to be finite differences. Do you know how to solve the fluid flow equation with finite differences? I see some yes, I see some no. What? You have done it?
Yeah, I had a course in undergrad.
Yeah? I still see that some people have not seen it, and this is something I really like to do. So let's do it one more time, okay? So finite differences, fluid flow. We're not going to solve the one for mechanics because that one takes a lot more of space to do, but it's basically the same. If you want a solver that solves elasticity equations and mechanics problem with finite differences, you should look for a solver called FLAC. That one is based on finite differences. The approach is going to be exactly the same, okay? But let's do it with the fluid flow equations that are a little bit easier. So this is tau, and I deleted this equation over there, but basically if we wanted to solve that, we have to put the Q1 over there. So this was K mu Laplacian of pressure. Pressure is scalar, and I'm missing the 2 over here. Equal to 0, right? And if I assume that this is a homogeneous medium, the K and the mu are going to be the same everywhere, and everything I have to solve is just this equation. That's everything I have to solve, right? So how do we implement this equation? If you want to implement it in finite differences, first of all, we need a grid. Can you guys see the grid from there well? So I'm going to call this grid in the direction I, where this is position I minus 1, position I plus 1. All right? And then, since this is a two-dimensional grid, we're going to solve the problem in 2 dimensions. It's a little bit easier than in 3 dimensions. This is going to be direction J. With this one is J, this one is J minus 1, and this is J plus 1. So over here, I have the element Ij, and since I'm interested in pressure, this is going to be the pressure Ij. And for example, over here, I'm going to have the pressure Pi plus 1 J. And the same for all the other ones, right? So how do I express a second derivative in finite differences? Let's say that this is going to be Pi minus 1 J. I'm going to go further on and call this difference in I delta X, and the difference in the grid in J delta Y. What is a second derivative in this case? Okay, so you're correct, but let's talk about the meaning. What is the meaning of a derivative? First of all, the meaning of a derivative, physical meaning, will be the slope, right? The slope of, in this case, the pressure field. And probably we can continue over here. And what is going to be the second derivative? If the first derivative is a slope of in this case, a pressure field, what is going to be the second derivative? The change of the slope in a given difference x, right? So if I wanted to see the change of the slope of this one respect to that one with this one respect to this, and it's going to be a change of the slope, the first one I'm going to have here is delta x, because this is a change, okay? The first, and now I'm comparing slopes. So I'm going to compare this slope to that slope. So this is going to be Pi plus 1 J minus y. I don't know why. It's too much mechanics. I write sigmas instead of p's, right? That's a p. That's a p. Pi J divided delta x, right? This is a slope from here to here. And I'm going to have to make a difference too. And now I have to subtract this slope. So Pi J minus Pi minus 1 J divided delta x. Those are the difference in the slope in a given distance, delta x. That's the second derivative. That is this guy. And if we want to do this one, we can do that one quickly. Since we know the structure of the other one is going to be very similar, delta y, and here this is going to be delta y, delta y. And now, what do I have here? J plus 1, right, minus pi j, and here I'm going to have pi j minus pi j minus 1, right? And those are going to be delta x and delta y squared later. And what about if I assume that delta x is equal then to delta y? So that's going to be in a square grid. I don't have to assume that, but it could be. It could be that I have that. If you know this, there are some terms that this one is negative here, but it's positive. Well, it's negative over there, right? So this is going to be negative and negative. Pij is again negative here, and now it's negative over there. So I have 4 Pij's which are negative. And on the other side, so these are the 4 Pij's. On the other side, I have the neighbors of Pij. And if you look at that, they repeat just once. So Pi plus 1 j plus Pi minus 1 j plus P j plus 1 I plus P j minus 1 I. And that's it. That's everything you need in order to solve this fluid flow problem with that equation. So how do you implement that? You can do it even in Excel. You can use in an iterative solver. You fix what are your boundary conditions, basically your pressures on one side of your domain, and then later you just tell that every cell is the average of the neighbors, and you make it run, and that's it. That's everything you have to do in order to solve this kind of problem. So for mechanics, it's going to be pretty similar, but now we have 3 unknowns. So you have displacement direction 1, displacement direction 2, displacement direction 3. So it gets a little bit more complicated, but not a lot. Again, if you want to solve these problems with finite difference, probably it's a good exercise to do it from scratch. For the pressure, it's very easy, but for mechanics, it's going to be a little bit more complicated. Probably you can go to some